examples, but today is going to be about deriving the rest of the rules. Why? Because if you forget them, I want you to be able to recreate it. And if you're ultimately going to go into HL math, you need to start realizing and seeing, as we're doing through this whole chapter of trig identity proofs, how to create and do a proof. These are more like derivations as opposed to proofs, but still. We've got the sine of alpha plus beta is equal to the sine of alpha. We'll just do the sum formulas. The sine of alpha plus beta is equal to the sine of alpha cosine beta plus cosine alpha sine beta. We've got the cosine of alpha plus beta is equal to the cosine of alpha times cosine beta minus sine alpha sine beta. And we have the tangent of alpha plus beta is the tangent of alpha plus tangent of beta over 1 minus tangent of alpha tangent of beta. We derived this one the other day from the sum and difference identities. And we're going to be using the sum and difference identities to literally derive every single formula you're about to see. So there is this family of double angle identities. So we're going to come up with the sine of 2 theta. Okay, what is that identity going to be? Well, you know how to figure out the sine of 2 angles added together. And is it not true that 2 theta can be written as theta plus theta? Of course. So we have the sine of theta plus theta. And what is the sine of 2 angles added together? Sine of the first, or theta, times the cosine of the second, cosine theta, plus cosine theta, sine theta. Well, yeah, if the 2 angles are the same, theta plus theta is 2 theta, then we have the sine of 2 theta is, well, I know this is sine theta, cosine theta, and we have a cosine theta, sine theta. The factors are not in the same order, but of course we know that multiplication is what? Commutative. So these are like terms, and we get the sine of 2 theta is 2 sine theta cosine theta. So with that example, take a minute, probably more than a second. What is the cosine of 2 theta? What is the cosine of theta plus theta? Anyway, here we go. The cosine of theta plus theta, what do we got?
So you can use that identity over there. It would be, it would be cosine of theta minus sine of theta, sine of theta.
Yeah. And remembering that where we have the sine of 2 angles added, we have that addition in the identity. But with cosine, when you're adding those 2 angles, there is subtraction, giving us
Cosine theta squared minus sine theta squared.
There you go. And this is a proof and a justification that we've got, and I'm pausing to say this and realizing the Pythagorean identities are not on the board. But we have another 3 formulas that we already know that's not up here, which are those Pythagorean identities. We've got sine of theta squared plus cosine of theta squared is equal to 1. And it's very, very common for students to think that if there's a minus sign here, that this comes out to be -1. And though I don't see it on the board, we just showed that the cosine of 2 theta is equal to cosine squared theta minus sine squared theta derived from the sum identity for cosine. So yeah, negative sine of theta squared plus cosine of theta squared is a very, very different value than just being, a hypothesized value of -1. What's the other 2 Pythagorean identities? 1 plus cotangent squared, okay. 1 plus cotangent of theta squared is equal to cosecant squared theta. And 1 plus tangent of theta squared is equal to secant of theta squared. And those will come into play as we continue today's journey. Now, I'm going to do this for you on the memorization test to remind you that there are 3 formulas for the cotangent of 2 theta. Which of these 3 you use if you're doing a problem that involves a unit circle and your answer is something like a 1/2 or square root of whatever, whatever, whatever. If you're doing a unit circle evaluation process, which of these 3 you use, it doesn't matter. But there are 3 versions of this double angle identity for cosine, and if you're doing proofs, it's going to be really important that you choose the most convenient of the 3. There is a version. We have the cosine of 2 theta is equal to cosine of theta squared minus sine of theta squared. There is a version that is only in terms of cosine of theta squared. How are we going to get there? Karina?
Well, sine of theta squared is 1 minus cosine.
And that's part of the reason I needed to pause and put these Pythagorean identities up here. We're going to do substitution and take out sine of theta squared and replace it with 1 minus cosine of theta squared. Distribute the -1, combine like terms, and we get 2 cosine of theta squared minus 1. So that is the second of our 3 identities. There is another identity that is in terms of sine squared. So work that out. Derive that for yourself here. So how are we going to write cosine of 2 theta in terms of sine?
You substitute the cosine square of theta with 1 minus sine squared.
So the cosine function's coming out. We've got 1 minus sine of theta squared getting substituted in for cosine of theta squared minus another sine of theta squared. And we get 1 minus 2 sine of theta squared. Now, we're going to have another double angle identity for tangent. I think we can just look up here. If this is the tangent of theta plus theta, then it'll be the tangent of theta plus tangent of theta. So what's our numerator going to be? 2 tangent of theta over 1 minus. Again, if this is theta plus theta, if these angles are the same, it's tangent theta times tangent theta, or tangent of theta squared. Bam! Nice. Now we've got 3 Pythagorean identities, 6 sum and difference identities, 1, 2, 3, 4, 5 double angle identities. All right, great. Well, there are also half angle identities. You may not realize it because we're just seeing these derivations for the first time, and we haven't worked with any of these identities yet. But the first identity is actually already up on the board. So let's try this. Now, this is going to be how it's written in the book. We want to find the sine of theta over 2. Again, building up our abstract knowledge, our sort of fundamental knowledge of algebra, not just doing straight memorization. Being able to create these formulas on our own if we happen to forget something. You still have to have a foundation to build off of. But the sine of theta over 2. Okay, so this is an angle measure. What do you put into a trig function? An angle. So if you see a trig function, no matter if it's a number or an expression, even if it's a simple or complex expression, if that expression is going into a trig function, it is an angle measure. So this angle measure is simply half, right? It's theta over 2. This is half the measurement of some other angle. Do we already have an identity over here that has angles and other angles that are half as big or twice as big?
The sine of 2 theta.
Yeah. The sine of 2 theta is equal to 2 sine of theta cosine theta. So this angle 2 theta is twice as big as these. Or these angles are half as big as that angle. But this is not a desirable identity to start with because you've got sine and cosine hanging out together. So how about this identity? The cosine of 2 theta is equal to, so a little bit of scratch work, the cosine of 2 theta is 1 minus 2 sine of theta squared. Okay. Well, what if I let x equal 2 theta? Then we've got the cosine of x is equal to 1 minus 2 sine of x over 2 squared. This double angle identity arguably is a half angle identity. It's just not solved for that smaller angle or the trig function that has that smaller angle. So we're just going to reorient the terms and factors and coefficients of this double angle identity and create our half angle identity. So we're going to subtract both sides by 1 and get the cosine of x minus 1 is equal to negative 2 sine of x over 2 squared. So divide by negative 2. Now I know the identity does not have a negative 2 in the denominator, so I'm going to bring this negative 2 and kind of distribute it through the numerator. And we have 1 minus cosine of x over 2 is equal to, now negative 2 divided by negative 2 is of course 1. So we have sine of x over 2 squared. And how do we get rid of the power of 2? We introduce our own even root. So if we introduce our own even root, we have to account for the positive negative nature of that. Or the square root of something squared is an absolute value function, which is actually creating the plus or minus nature. So our first identity, our first half angle identity is the sine of theta over 2 is equal to plus or minus the square root of 1 minus cosine of x over 2. Now, whether you use in your final answer the positive or negative solution is going to be dependent on what quadrant theta over 2 is in. You know, that's kind of smashed together there. If theta over 2 is in quadrant 1, obviously your sine value is going to give a positive answer. If theta over 2 is in quadrant 3, you're going to want to use the negative answer. So yes, it's plus or minus, but sometimes we're only going to be concerned about using one of these two signs dependent on the quadrant, the location of the terminal side of this half angle measurement. What is the cosine of theta over 2? What double angle identity are we going to start with? Cosine of 2 theta is equal to 2 cosine theta minus 1. If we let x equal 2 theta, just to make this look a little bit different and match the form of the identities in the book, we have the cosine of x is equal to 2 cosine of x squared, x over 2. squared minus 1. Add 1 to both sides, divide by 2. And how do we get rid of the power of 2? Square root. So we have the cosine of theta over 2 is plus or minus the square root of cosine of x plus 1 over 2. Now that we have the sine of theta over 2 and the cosine of theta over 2, what would be the tangent of theta over 2? You're getting ahead of me. It'd be sine of theta over 2 divided by the cosine of theta over 2. And then, yes, ma'am, you're absolutely correct. That means that the tangent of theta over 2 is going to be, all right, so that is going to be, help me out.
Square root of 1 minus cosine theta over 2.
So the square root of 1 minus cosine theta over 2 divided by,
Square root of cosine theta plus 1.
yeah, I'm gonna, for the purpose of where we're going, I'm going to swap the order of that addition. 1 plus cosine theta over 2. So the tangent, of course, tangent regardless of the size of the angle is sine over cosine. Well, you have a division of a fraction. If you want to instead show a multiplication of the reciprocal, you would have the square root of 2 over 1 plus cosine theta, which then opens the door for the common factors of 2 to cancel out across that multiplication. And we get the tangent of theta over 2 is plus or minus the square root of 1 minus cosine theta over 1 plus cosine theta. And if it's been more than a couple of days of me saying this identity out loud, I forget, I doubt myself, and I forget, is it the plus or the minus, like the orientation of the addition and subtraction in this identity. So I pretty much have to do these derivations to make sure I know these signs correctly. There is a tangent of theta over 2 identity that has just the sine of x in the denominator. So knowing that the tangent of theta over 2 is plus or minus the square root of 1 minus cosine theta over 1 plus cosine theta, given this, and knowing that there is a version of this identity with just sine in the denominator, take a minute, even though I'm going to definitely run out of time, but take a minute and think about how you would make this show up. You've done some proofs now. How would you go from this expression to an expression that just has sine in the denominator? And do note, I did not write a square root. So something has to make that square root go away. So when you have these Pythagorean identities that are given as a sum of squares, they lend themselves to going into a difference of squares. And that difference of squares, you know, a plus b times a minus b is a squared minus b squared. So a difference of squares is created when you multiply two conjugates together. Like Carl said, he knows that 1 minus cosine of theta times 1 plus cosine theta is 1 minus cosine theta squared. And that's exactly what we're going to do. We're going to multiply this expression by a form of 1. So it'll look different but not change its value, just like you do when you add fractions. So we're going to multiply the numerator and denominator by the square root of 1 minus cosine of theta. And when you do that, you get plus or minus the square root of 1 minus cosine theta times 1 minus cosine theta is 1 minus cosine of theta squared. I only know not to expand that because I worked with these identities for years and years and years, so got a little bit of an advantage. In the denominator, we have 1 plus cosine theta times 1 minus cosine theta. These are conjugates, which means that those are the only two two-term factors that you can multiply together and not get a middle term. So this is going to come out to be 1 minus cosine of theta squared. Well, what's 1 minus cosine theta squared? Sine of theta squared. So we're getting closer to the denominator that I told you need. So we have plus or minus the square root of 1 minus cosine of theta squared over sine of theta squared. Now, if you apply the even root to the, what does the square root do to both the square in the numerator and the square in the denominator? When you square root a fraction, you're technically square rooting both the numerator and denominator separately. So what do these powers of 2 and square roots do? They cancel out, and you get, as a final answer, 1 minus cosine of theta over sine of theta. This version of this half-angle identity for tangent is the much preferred version for doing unit circle type questions where your answer is going to be just a numerical value. The only time I ever really use this first version of the half-angle identity for tangent, where you have the square root of 1 minus cosine theta over 1 plus cosine theta, the only time I really use this is in trig proofs. If I'm evaluating the tangent of theta over 2, I'm using this version. The denominator is the simplest you can get. Now, there is, I'm not going to walk through this whole thing because of time, but there is another version of this identity where sine of theta is in the numerator, not the denominator. Any guess? Charlie? So instead of multiplying by the conjugate of the denominator, like we just did, you multiply by the conjugate of the numerator. And when you get done with that, you're going to get sine of theta over 1 plus cosine theta. That's 16 identities derived from 2. We had 2. Okay, I guess maybe we had 5, the Pythagorean identities. But actually, if you have the first Pythagorean identity and the sum identities for sine and cosine, if you know just those 3, you can derive all these other ones. There are some power reducing formulas that come in super handy in calculus. We're not in calculus yet. In this format, this is not a doable problem. You cannot integrate this question. But if you use a power reducing formula, you can. So on the board, is there anywhere that relates a cosine to a power of 2 to a cosine of power of 1, even if the angle measure is different? The cosine squared theta is equal to, in some term, of cosine of 2 theta. So if I saw this on a calculus test, I would take the cosine of 2 theta, which is equal to 2 cosine of theta squared minus 1, and write it as the cosine of 2 theta plus 1. Divide both sides by 2 and get 1/2 cosine of 2 theta plus 1 is equal to the cosine of theta squared. And where this is a problem you cannot do in calculus, this is a question that you can. Now, what that looks like is beyond the scope of this course, but not possible, possible. So there are 3 more, and I don't have these to memory. I'd have to derive them, but we're running out of time. I've got, maybe I can get a couple of these up quick. Cosine of theta squared is cosine of 2 theta plus 1 over 2. And the sine of theta squared is 1 minus cosine of 2 theta divided by 2. And the tangent of theta squared is 1 minus cosine of 2 theta over 1 plus cosine of 2 theta. That should